About section 4 in chapter 6, taking the derivatives of logarithm functions, and we'll look at the integrals too. Okay, so basically, and you could probably look at I think the book shows this proof of this derivative, but the derivative of ln of x, which is the natural log of x, is 1 over x. So anything, if I'm taking the derivative of anything other than that, that's when I'm going to have to do chain rule. Okay, so here, if I just take the derivative of just x, it's 1 over x. But if I do anything other than just plain x, that's when I'm going to have to do chain rule. Okay, so I'm going to let u equal x cubed plus 1, and then I can go ahead and take that derivative, 3x squared. Right, so that's the derivative of u. And so you take the derivative of the outside, which is just ln. So the derivative of ln is 1 over x, but here would be the derivative of ln of u, which is just 1 over u. And now I can go ahead, so that's the derivative of the outside, and now I just leave that inside alone, right? And I times that by the derivative of the inside, right? So I'm going to take 1 over u, and I'm going to times that by the derivative of u, which is, I'll just say u prime for now. So then I can plug u back in, which is x cubed plus 1. And then I can go ahead and times that by the derivative of u, which is 3x squared. You don't have to use u. I won't use u in the next one, but you don't have to. Okay, and then you can go ahead and just put that over top, 3x squared over x cubed plus 1. And so there's the derivative. So that is the derivative, taking the derivative of ln of x cubed plus 1. Okay, so that's the derivative of it. All right, here's another example. So here I just take the derivative of the inside, or derivative of the outside, which is 1 over sine of x. And then I times that by the derivative of the inside. The derivative of sine x is just cosine x. So this is just cosine x over sine x, which can be simplified to cotangent x. So there's the derivative of it, cotangent x. So it's basically just chain rule. Anytime it's not just plain x, you're going to have to do chain rule for the derivative. So here's the basic thing. Anytime you want to take the derivative of ln of another function, so when you have something other than x in here, it's basically just the derivative of that inside over that inside. So it looks like that. So that's the derivative of anything you're taking the natural log of, if you're taking the derivative of that. Okay, so here's a couple more examples for you. And so here we can rewrite this as ln of x, and that's being raised to the 1/2 power. And so then we can go ahead and apply our logarithm rules. Well, actually, I can't apply my logarithm rules because I'm not taking the ln of x to the half. I'm taking ln of x and raising that whole thing to a half. So this is different from ln of x raised to a half. That I can move out in front of the log, but this one I can't. So that's not true. But what I can do is let u equal ln of x, and then just take the derivative of u to the 1/2, which we know that is that's the derivative. And now I just do chain rule, right? So u is ln of x, well, the derivative of that is 1 over x. So now I can just apply chain rule. Derivative of the outside, which is raised to the 1/2, is 1/2. Leave the inside alone. Drop the power by 1, and then times that by the derivative of the inside, which is 1 over x. And then basically you can just simplify this. 2 goes on bottom with this x goes on bottom. This is a -1/2 power, so that brings it down to the bottom, which becomes a root on bottom. And then this x and 2 are on bottom as well. And so there's your answer for that one. All right, looking at this one, it's more complicated because the derivative of the inside is going to have to be quotient rule. All right, so take the derivative of the outside, because you're taking the ln of this. Derivative of the outside is 1 over x. So that's 1 over x plus 1 over square root of x minus 2. And then the derivative of the top is taking the derivative of this, which is going to be a lot. Okay, so that's quotient rule. Oops, that's quotient rule. Okay, so we'll go ahead and do quotient rule on that one. So that is the top. And we'll rewrite that square root as a x negative 2 to the half. So that is the bottom, which is a half power, times the derivative of the top, which is just 1, minus the derivative of the bottom, which is chain rule, but the derivative of the inside is just 1, and then times the top, which is just x plus 1. Okay, so it's all multiplication there. Okay, and then all over this thing is all over the bottom squared, so that is square root of x minus 2, square root of x minus 2 squared, so that square and square root are going to cancel each other out. Okay, so now let's go ahead and simplify this. So we have x to the negative 2 raised to the 1/2 minus, well, when we simplify this, we can take out that 1, so we still just got 1/2 x minus 2 to the negative 1/2, and that's times by x plus 1. And then it's all over just x minus 2, because the square root and squared get canceled out. And then, so we can keep on going here. We can go ahead and just factor out an x minus 2 to the negative half power, because if I factor out a negative 1/2, this will just become 1. This will cancel out. When I cancel out here, I take 1/2 minus a minus 1, which is a plus 1, so I just get x minus 2 here when I factor that out. So I'm going to factor out an x minus 2 to the negative 1/2. And so this term will become x minus 2. This one's going to cancel out to 1, so I just get left with minus 1/2 times x plus 1. And then on bottom, I still have my x minus 2. Okay. All right, now we can just do some simplifying here. We can go ahead and distribute that negative 1/2. And so we just get negative 1/2 x minus 1/2. And then we have the x minus 2. And then x minus, we can just bring this x minus 2 down to the bottom. So we get x minus 2 to the positive 1/2 times x minus 2. And so those are the same base. So we can go ahead and add those exponents. So we get x minus 2 minus 1/2 x minus 1/2, which we can simplify that, right? Minus 2 minus 1/2. It's minus 3/2, right? So minus. Oh, and we can do those x's too. Let's go ahead and simplify it all, right? Might as well. So we have x minus half of x, so that's 1/2 x. We have minus 2 minus 1/2. That's minus 5/2. And then all over, we can join those two bases together by adding their exponents, and we get 3/2. So here we have this, and then we can go ahead and simplify that even further by having to deal with this, just taking out that 1/2. So we can factor out a 1/2 out of the top. Come on, move down. There we go. So 1/2 out of the top, we get left with x minus 5 all over x minus 2 raised to the 3/2. That 1/2, it's the same thing, it's just putting the 2 on bottom. And so we get x minus 5 over 2 times x minus 2 raised to the 3/2. So that was our derivative. That was our derivative of the x plus 1 over square root of x minus 2. That was the derivative of that, right? So that's not where we're completely done. So that's the derivative of that. So now I can go ahead and take this and times that by my derivative of the inside was this. So basically this one's just going to go on top. So the x minus 5 over 2 times x minus 2 to the 3 halves. That's going to go on top where the other one was x plus 1 over x plus 1 over square root of x minus 2, which we can rewrite that as to the half power. And then when I'm dividing by a fraction, I'm multiplying by the reciprocal. 3 halves there, so that'd be x minus 2 on top for x minus 1. So those x minus 2's, right, this is the same as 4 over 2, and we have the same base here. So we can go ahead and subtract those, and we just get a half. So 4 halves minus 3 halves is just 1 half. So this becomes x minus 5. Actually, that's not 4 halves, sorry. Erase that. That's 1 half. This is a half. You're probably confused by that. So 1 half minus 3 halves is just a negative 2 over 2. So I can just bring that down, right? Because this minus this, 1 half minus 3 halves, it's just a negative 2 over 2, which is just a negative 1. So I can just put that exponent on bottom. So I get 2 over x minus 2, x minus 1. So there is our answer to that. The whole thing is right there. You could also do it by logarithms. So here's our original d over dx of, this is actually probably the easier way. You won't see it match up exactly to this without simplifying it further, but our properties of logarithms suggest that we can go ahead when when we're taking the log of a quotient, we can rewrite that as the subtraction of the two logs, top minus the bottom, with that same log. And then so I can just take the derivative of each one of these, which is just 1 over x plus 1 minus, this I had to rewrite as a half power, right? So here I'm going to have 1 over x minus 2 to the half, and then the derivative of the inside, which is chain rule, which we already did before. So that's 1 half x minus 2, like that. And then this would just simplify. Eventually this would simplify to that same thing as this right here, right? We have this on bottom. We have this x minus 2 on bottom. This 1 half, I can move that 2 to the bottom basically. And then, but you're going to have to find a common denominator here. And so when you do that, find that common denominator and put those together, it would eventually simplify to this. So whichever way is easier for you. All right, let's go ahead and look at the integrals. So if the derivative of ln x is 1 over x, that means the integral, the antiderivative of this 1 over x is ln. And it's always absolute value here because I can't take the log of 0 or any negatives, right? So if I have a problem like this, I can't take the integral of this. I have to make it look like this, right? So I'm going to have to do u. So I'm going to have to let u equal something where I get x over 1 over x. So that means what I have to get here, since I'm using u, is something like this, 1 over u. So I usually typically let u equal the bottom. Okay, and then always substitute it directly in. X over u dx. Okay. Now rewrite this so it looks like this. 1 over u, and then that would be times by x dx. So basically, my derivative needs to look like that. So my derivative u needs to look like that. So we'll take the derivative of u, du, let's do du, equals 2x dx. So if I divide by 2, there it is. So 1 half du is equal to x dx. So this x dx is 1 half du. 1 half du. I can bring that 1 half in front. Now I can take the integral of this, because now it's in terms of u. And now we can go ahead and the integral of that is ln of u, and it's the absolute value of u, plus c, and then 1/2 out front. And so there is our answer. And then we can go ahead and enter in back in our u, absolute value of x squared plus 1 plus c. And then here, because this is always going to be positive, x squared plus 1, right? X squared plus 1. Graph looks like that. It's always going to be positive. So you could drop the absolute value bars. All right, the definite integral. So here again, I need to look like this, right? So that means I'm going to let u go ahead and equal a little bit different here, because if I let it equal just plain x, the derivative of that is just 1, right? And that 1's not going to cancel with that. So I can't let u just equal x. I'm going to let u this time, you just kind of play around with it, let u equal ln of x. And the derivative of that, we know, is 1 over x. Okay? And so now just go ahead and replace that. From 1 to e, the ln of x we let equal u. Now rewrite this, because we know the integral of just plain u, right? Okay, so we can take that. That's fine. So now we just need to replace this. Well, that's exactly what my du equals. So 1 to e, integral from 1 to e of u, and that is just u 1/2 times u squared, right? And that is from 1 to e. Now be careful, I don't plug in 1 and e, because 1 and e actually goes in where there's an x, right? So I need to replace my u first. So my u was ln of x, and then that is being squared. And now I'm taking that from 1 to e. So now I can plug in my e. ln of e, that's just 1. ln of e minus ln of 1, and ln of 1 is just 0. Oh, those are being squared, sorry. That's being squared, and that's being squared. Okay, and then that's being times by 1/2. So ln of e is just 1. So 1 squared is just 1, and then equals negative. Ln of that's just 0. 0 squared is just 0. And so I just have 1/2 minus 0 is just 1/2. So there's my answer, 1/2. So you got to play around with that substitution rule. Let u equal something, take the derivative of that. Will it cancel out? If it doesn't, you got to substitute u in for something else. All right, so there's no direct integral for tangent. All right, so we want to substitute in tangent. What is tangent? Tangent is sine of x over cosine of x. So you got to get it a little tricky here. And again, we're talking about the derivative, the integral of 1 over x. Right? We know that answer is ln of x. Right? So I need to turn this into 1 over x. Right? So I'm going to let u equal one of these and see if it works out, right? So I'm going to let u equal cosine of x, because the derivative of cosine of x equals negative sine x. Right? So then if I put that in my integral, that'd be sine x over u dx. I can rewrite that as 1 over u times sine x dx. So then I need to let my derivative equal that, which is almost, I just have that negative out. So if I multiply both sides by a negative, I get that. And then I can replace it. So that negative is just going to come out in front of the integral. And now we can go ahead and take that integral of 1 over u, which is ln of u. We just have a negative out front. And then I can replace my u. Extend. And my u is what? Cosine x? And it's just negative, right? So now we can use our properties of logarithms. Say if I have something on the outside, I can rewrite that as a power. So negative 1 power. And negative 1 is just the reciprocal. So that is 1 over cosine x. And 1 over cosine x is secant. So tangent, the integral of tangent x dx equals 1 over secant x plus c. So there's the integral of tangent. So now you can use that. Okay, a couple other properties that you can use. If I'm taking the derivative of a log with base a of x, then the derivative is always going to be 1 over x times ln of a. And so here's an example. Here would be my a. Here would be my x. So my answer to this is 1 over my x, which is 2 plus sine x, times the ln of my a, which is 10. So there's my answer to that. And then I have to take, because this is not just plain x, that means I have to do chain rule, so I have to take the derivative of this. So I'm just going to times this by the derivative of the inside, which is just cosine x. So cosine x over 2 plus sine x times by ln of 10. So there's my answer to that. So basically you just take, anytime it's not just plain x, you're going to have to do chain rule. So you have to do the derivative of that. So just x prime over, this answer will always be x prime over x times ln of a. So you could do it like that. This is how this answer would be interpreted other than just x. Another one is this one. So if I take the derivative of just a base raised to x, then it'll always be this. And again, if I'm doing something like this, where I have this function up here, I'm going to have to take chain rule. I have to do chain rule. So eventually this is going to be times by the derivative of x. Okay, so this is, here's my a, so it'd be 10. My x just stays x squared ln of a, which is just 10. And then I got to times that by the derivative of my function up top here. So that's just 2x. And so there's my answer. You can rearrange it if you want to. You could do 2x, 10 raised to the x squared, ln of 10 is fine too. Okay, so there's that rule, and then we have this one as well. The integral of a raised to the x is a to the x over ln of a plus c. And so that's how that one looks. So if you're taking the integral of anything raised to the any base raised to x, you can rewrite it like that. Okay, so, and then the last part is logarithmic differentiation. I can't even say it now. But there it is, even though I probably spelled it wrong. But here, basically, we're trying to solve. Remember, these ones we're trying to solve differentiate. So that one we're solving for y prime. Okay, so this one you want to do the log properties first. So log properties, take the log of both sides, ln of this big massive thing here. Okay, and then I can use my log properties. Log of the top minus log of the bottom. And now I can go ahead and take the derivative, right? So I'm going to take the derivative of both sides. So this one, the derivative of that is just 1 over y times the derivative of y, because normally it's in terms of x. So because it's in terms of y, that means I need to do chain rule, right? Anything in terms of y, when you're taking the derivative, when you have a y in there, you're taking the derivative in terms of x, you have to do chain rule. Okay, and then we can take the derivative of these separate things, each one of these. So when we're multiplying, we can use our properties again, and we can separate that by addition, which just makes these derivatives a lot easier. We don't have to do product rule. And this one we are going to have to do chain rule on that one. Okay. All right. So now I'm still taking the derivative of this whole thing. So I still need to take the derivative of that whole thing. So that is 1 over x times 3/4. We're just using that property, the derivative of ln of x raised to anything here, because we can just bring this out front, use the property logs. So that's 3/4 ln of x, and I'll just take the derivative of ln x, which is just 1 over x. Okay, this one, you can rewrite this as a half power. I can bring that half out front. So that half is out front. Now I can just take the derivative of x squared plus 1, which is the derivative of that is just the derivative of the inside, which is just 2x over the inside. So I get that. Minus, here it's going to have to be, I can take that 5 and bring it out front, right here, times the derivative of this. Remember, it's just what I'm taking the log of on bottom times the derivative of the inside, because it's just chain rule, which is just 3. Okay, so then we can simplify all this, because this all equals y prime over y. And I'm just solving for y prime, right? So I'm going to simplify all this stuff and multiply both sides by y. So I'm going to multiply this whole thing by y and simplify. So y is on the outside. I get 3/4, and x is on bottom here. These 2's would cancel. This is just multiplying. So I get x over x squared plus 1. Then here, I just have negative 15 over 3x plus 5. Okay, and so then you could, if you wanted to, we know, well, what you need to do here is we know what y equals from the very beginning. Y equaled x to the 3/4 times the square root of x squared plus 1 all over 3x plus 5 raised to the 5th. And that's being times by this. And I don't care how sloppy this works, but you do have to plug in that. You do have to plug in that what y equals, because we actually know that part. So there's how complicated it looks. It's fine how complicated it looks. Now, if they give us some x value, x equals something, we can go ahead and plug in those x's into all these spots and simplify to figure out what y prime is. So a little complicated, but that's how you do it. So here are the steps to do it. 1, take natural log of both sides. Take ln of both sides. 2, simplify your logs. Use log properties. Use log properties to simplify. Then 3, you want to differentiate. See, I said it right there. Implicitly. With respect to x. Basically what that means is you're taking the derivatives with respect to x. It means in terms of x. So that means whenever you have a y, you're going to have to do chain rule. So whenever you take the derivative of y, it's y prime, right? Or if I take the derivative of y squared, that'd be 2y, y prime. I have to use chain rule on that. And then 4, solve for y prime, replace y for what it equals if you have a y. Okay, so that's how you do it. All right, 30 minutes. Perfect.